All right. Hello. Thank you for coming. I am Brett Benish. I am the chair of mathematics here. You all braved the great blizzard of 2019 to come here, and I appreciate that. It had yellow-orange dust from Texas that stuck to my driveway. So you must really love mathematics to come out here. So I love this conference. Not to brag, because my department puts it on, but it's a great celebration of undergraduate research, which I love, and also it's a good community building kind of activity for my colleagues at schools I don't get to see all that often, but who I really love. This conference was made possible tonight by the mathematics department here, but in particular, I'd like to mention Sunil Chetty and Chris Nairn, Jennifer Galovich, and our administrative assistant, Suzette Ellinger. And they did a lot of work to put this on. I can only imagine how much work a conference is, but we really appreciate it. And they created an opportunity for me to see a whole bunch of great mathematics talks tonight. I was really impressed at what I saw tonight. I'm really looking forward to what we have in store for tomorrow. And I'm really excited to see what is going on later tonight, including right now. So I would like to introduce you to Jennifer Galovich, who's going to talk about the main event.
First of all, I'd like to, I'm on, right? This is working, okay. I'd like to congratulate the student speakers that we heard earlier this evening on their excellent work and for sharing that work with us. So let's give them a round of applause. And not only do they get a hand, they get a free book. So if you are a student speaker, then ask any St. John, St. Ben's person where the Math Skills Center is. It's basically down that hallway, last door on your left, and there are some new books in there, and you may choose one. So that's your door prize, if you like. Oh, and okay, and now it is my pleasure to introduce my friend Talitha Washington, who is our speaker this evening. Dr. Washington earned her bachelor's degree at Spelman College in Atlanta, completed her master's degree in doctoral work at the University of Connecticut. She began her teaching career at the College of New Rochelle and then moved to the University of Evansville in Indiana, where, among other things, she ran for the school board, early activism. For the past 7 years, however, Dr. Washington has been on the faculty at Howard University in Washington, D.C., I have written, she's currently on leave from that position. I've learned that the right government speak for this is that she has been detailed to the National Science Foundation, and she serves the mathematics and science professions as a program director for education and human resources. Dr. Washington is no stranger to undergraduate research. She did her own senior thesis at Spelman on pricing models for stock options, which sounds like a lot of heavy-duty differential equations to me. True? Okay. She continued her interest in modeling in her graduate work, where she studied protein-protein interactions. In general, she is interested in nonlinear models, and we will hear more about that tomorrow morning. It goes without saying that Dr. Washington is passionate about mathematics and teaching mathematics, but she is also passionate about lifting the curtain on all those hidden figures in science and mathematics, teachers and researchers whose work has often gone unnoticed or has been marginalized. Many of us have seen the film Hidden Figures. You may have seen in January the shorter film Outlier that we showed, and on that latter one, Dr. Washington was one of the talking heads, consultants for the Outlier film. And tonight she will share with us the mathematical story behind the Hidden Figures film. So let's welcome Talitha Washington.
All right, well, thank you, and it's great to be here, snow and all. And I just want to publicly say a huge thank you to Sunil for informing me to wear boots. So that was fantastic, properly attired here. So as she said, my name is Talitha Washington, and I'm just going to walk you through the mathematics of Katherine Johnson and how the mathematics came into play with the Hidden Figures movie. So the Hidden Figures movie featured 3 African-American mathematicians and engineers. So if you look here on the left, Dorothy Vaughan, she was portrayed by Octavia Spencer. Katherine Johnson, who's in the middle, she was portrayed by Taraji Hansen, and Mary Jackson was portrayed by Janelle Monáe. So, and of course, we got to get the math right. So the mathematical consultant for the movie was Rudy Horn, And he's shown here on the left with the author of the Hidden Figures book, Margaret Shetterly. But before I dive into things too deep, as any good abiding of governmental policies person would do, all of my opinions are mine and do not represent the views of any organizations. And there's a shout out of love for NSF for funding this through the IPA program. So, okay, got to get that out the way. So in being here tonight, it's kind of fun because this is the Pi Mu Epsilon program from when I got inducted as a Pi Mu Epsilon person, like, I want to say a couple years ago, but maybe a couple decades ago when I was an undergrad. So this was on April 12th, about the same time frame, back in 1994. So my name's over here. And then my speaker, the person who gave my address, was J. Ernest Wilkins. J. Ernest Wilkins was the seventh black to earn a PhD in math. He was 19 from the University of Chicago. By the time he was 21, he worked in the UMet lab. Remember the one that worked on the Manhattan Project? Mm-hmm. At the age of 21, he saw his work drop bombs, Hiroshima and such. So actually, in a couple of weeks, I'm going to talk about his work and the mathematics he used at the upcoming National Math Festival. So it's interesting how this kind of all wraps in together, even with the snow. So just wanted to put that out there. And actually, so I should say, you got to be careful, who you keep for company, because down here, Sri Whitaker, she's still a good friend of mine. She lives in DC, has her own consulting firm, statistician. John Harkless, colleague of mine at Howard University, computational chemist. I could go on, right? So it's neat to see that I've maintained these relationships over the year. So I come from Howard University, and how many people can say that their school was named by a person who is a mathematician? So that was me. So General Howard is actually, this is our original seal, and here's General Howard here, shown kind of above the earth. The slogan is equal rights and knowledge for all. On the left-hand side, you have two natives, one female and male. On the right-hand side, you have two Africans, one male and one female. So Howard was actually started by an act of Congress, so we're a federally chartered institution. And they had no limitations for students with regards to sex or race. And the first students of Howard were actually, I think, 4 or 5 white females of the founding members. So those are actually our first students at the university. It's a historically black university, so the mission is to serve black Americans. So just got to put the mathematics out there. So the Hidden Figures, how did this all come about? Well, some years ago, I had the pleasure of meeting Margaret Shetterly at the Joint Mathematics meeting. And she grew up in Hampton, Virginia. NASA's nearby, all these scientists. Didn't know what people did, was a grown-up, talking to her dad, and her dad was talking about a Sunday school teacher and the science that the Sunday school teacher did, and she was like, wait, what are you talking about? Like, who are these, what did they do? And she became intrigued. She never knew really what these people in her community did. She knew they were scientists, but nobody really told their story. So she started writing a book and doing the research. Actually, the Hidden Figures book was her first book. And it took her 3 years to do the work to actually get it all done. Fox actually bought the rights of the book to make the movie before it was finished. So it was kind of like a play going up. So just in case, I'm just going to show a snapshot of the movie. Here. Okay, let's see how this goes.
Hi, I'm Taraji Hansen. In my new movie, Hidden Figures, we learn about the brilliant African-American women who used their brains to make space travel possible. Their groundbreaking accomplishments are an important reminder for all of us to learn STEM: science, technology, engineering, and mathematics. These skills will make it possible for women and minorities to get careers we've only dreamed of. Like the women of Hidden Figures, you too could change the world.
Equilateral, isosceles, tetrahedron.
I've never seen a mind like the one your daughter has. You have to see what she becomes.
Move like that.
Katherine, we all gonna end up unemployed riding around in this pile of junk.
You're welcome to walk the 16 miles.
Or sit in the back of the bus.
You kiss me up.
You have identification on them?
We're just on our way to work at NASA, sir.
I had no idea they hired.
There are quite a few women working in the space program.
You know what we're doing here? We're putting a human on top of a missile, shooting him into space. That's never been done before. I need a mathematician that can look beyond the numbers. Math that doesn't yet exist.
You have someone?
Running what I'm playing.
Catherine's the gal for that. She can handle any numbers you put in front of her.
You're a computer at NASA. They let women handle that sort of...
Yes, they let women do some things at NASA, Mr. Johnson. And it's not because we wear skirts. It's because we wear glasses.
You've been gone for 300 hours.
Was Mama gone for 12 and a half days?
No, but it felt like it.
In 14 days, astronauts will be here for training. Everything we do can matter to their wives, to their children. I believe it's going to matter to the whole country.
My gals are ready.
There's no protocol for women attending.
There's no protocol for a man circling the Earth either, sir.
We all get there together, we don't get there at all.
Let me ask you, if you were a white male, would you wish to be an engineer?
I wouldn't have to. I'd already be one.
Don't you know that we're able?
So Taraji Hansen at the beginning of the movie, of course I have to say, she's a Howard graduate, right? Shameless plugs, right? So, but that kind of happened by accident. She's from Oxon Hill, Maryland, which is right outside of DC, south of DC. And her first undergraduate experience was at North Carolina A&T, which is a historically black university in North Carolina, which is the top producer of black engineers currently. She was an electrical engineering major. She took pre-calculus. She kind of failed. She had to go back home. So she came back home to the DC area, found herself at Howard University in the theater department. Now, note that when she was in high school, she tried to get into a performing arts high school. She couldn't get in. So now she finds herself knocking at the door at Howard University theater department, where you have Felicia Rashad, Debbie Allen. They all come from Howard, right? Black Panther. I could go on. I'm gonna stop there. Us? Okay. Stop. But she found herself at Howard, and she went to the theater program, and then she just blossomed into this career. So it's interesting to see her first passion, electrical engineering, kind of woven in with her current passion of acting. So it's just an interesting story. So you never give up. So remember when she was running across campus? And this also is the building here. This is on Morehouse College campus, which is a historically black college in Atlanta. And here you see the pictures, but you got to get your Hidden Figures photo shoot. Remember, I don't know, if you saw the movie, this is outside the West area computing, where they would go to work. And so I had to do my photo shoot as well. So that's on the Morehouse College campus. Yeah. So the math in the movie, they had to get the math right. What happened was, so why did they film this at Morehouse, of all places? Wynn Thomas was the production designer. He's the first African-American production designer. He worked on a lot of Spike Lee films, like School Days, which actually was filmed at Morehouse at one time. He called the math department at Morehouse and called Dwayne Cooper and said, I need a mathematician because we need to get the math right in this movie. So as any good chair would do, he calls his applied mathematician and says, Rudy, I need for you to, be the mathematical consultant for this film. Nobody knew about the book, right? I didn't know. Nobody knew about Katherine Johnson. I didn't know. Rudy said, I have to teach linear algebra. I don't have time. I have all my students. The professor life, right? You want me to do one more committee work, right? Why? But as any good chair would do, Dwayne said, hey, Rudy, I really need for you to do this. Just do what you can. Rudy said, okay, fine, I'll do it. And he dove into it, and he just really fell in love with the whole story and really had a great time. So this is me with Rudy, maybe some years ago. He was at the IMA, Institute for Mathematics and Its Applications, and I was walking down the hall, and there he was. I actually knew him since I was a graduate student, and we got our PhD in the same year. He initially started out in physics. That didn't go so well. But of course, mathematics saves people, so he became a mathematician. Right? Yeah. So you can see the interplay between the physics and the applied math in the movie that's needed for, in the mathematics that's needed for this movie. So as any good researcher would do, he said, okay, what's going on with this planetary mechanics? A lot of the mathematics that he incorporated into the film came from this book, Hypersonic and Planetary Entry Flight Mechanics. So I remember I met with him and he said, oh, this book's really expensive. I was like, no, I found it for $30 on Amazon. It's actually a really good book. It's a nice combination of Calculus 3, but in the spherical coordinates, because Earth is kind of round, right? So spherical coordinates in Calc 3. But then you also have a scientific computing aspect, because you'd want to do approximations, and you also have differential equations in there. So it's a nice interplay of all of those three. His primary job was really to help the actors put the math on the screen. So we do math because that's just what we do, right? It's our bread and butter. We speak it, live it, breathe it, what have you. But if you're an actress talking about mathematics, this is not something that you do. He actually had to teach them how to talk math, how to do math, and they learned it like it was script. Just like you learn a script, like you learn your lines. We just like it because it's fun and exciting, right? But they actually, so he worked alongside Taraji Hansen and the other people in the movie. And here's him with the director, Ted Melfi. So he really had, they said, okay, here's the scene, what's the math? He had to say, okay, what would that be and what would it look like? So here's Rudy in his own words.
This is Taraji P. Henson's character, who plays Katherine Johnson in the film. There's the space physics group that she works for, but that set, they actually were building from basically February all the way through late April, early May. So a lot of the math scenes were there, and there was those math scenes when the young Katherine died at the beginning. So a lot of my work was kind of at the beginning of shooting.
And at the end.
And at the end of shooting. So that made it kind of nice. And then there were a few other times I had to be on set for other scenes, but they were able to accommodate my schedule, and to my surprise, and it worked out.
So he was able to, that's Rudy, he's just that guy. He's from the south side of Chicago, and he's just always bubbly and happy.
This is...
Oh. Okay, so what's the era at that time? So Sputnik 1. So imagine, we're in a race with the Soviet Union to get something into space. That's our frontier. If let's say if the Soviet Union gets into space first, they could drop bombs on us. Back in the days, they used to have drills. Some of us in the room may remember. Duck and cover? Yeah, duck and cover was a thing. So on October 4th, 1957, they beat us. They successfully launched a Russian spy satellite Sputnik 1. And then they turn around on November 3rd in 1957 and put an 11-pound dog, Leica, up, and they call this dog Mutnik, Sputnik, Mutnik. You'll get it later, right? And so the United States, they were very happy that, the Soviet Union was getting things in space because they're thinking bombs are going to be coming down. So the United States at that time, they were scared. There was a lot of tension. And we needed to get up into space, and we needed to do it quickly. So we have NACA at the time, which later becomes NASA, and we need to figure out how to take over, let's say, the outer space. So they do get John Glenn out there, finally, and of course, what does it for them? Mathematics. It does it for everybody, right? Math is good for everyone. So how did they do that? What are the things that they used, or what are some of the concepts that they used to get the Friendship 7 up there in space, and then also back down safely? So imagine, this is Earth, you're somewhere over here. Well, maybe over here, right? I'm still in DC, apparently. So if you throw a ball up in the air, it's gonna come back down. And if you throw it to your friend, it'll come back down, and it'll follow like a parabolic orbit, a parabolic path. But let's say you're kind of up high enough and you throw it so that object is it's being pulled down by gravity, but it just keeps missing the Earth. So it just is in free fall around the Earth and starts orbiting, right? So we can call that an orbital velocity. So what's a way we can think about this? Well, imagine that the circle is the Earth and O is the center, right? We got to simplify, that's what we do in math. And the distance from, let's say, the point O to point A is R, and similarly, the distance from O to B is R. And here we have an angle theta. So let's say your object is following the path, orbiting around. And here we have velocity vector A and velocity vector B. Well, we can extend this line back, and we have a nice quadrilateral. And we know the sum of the interior angles is Okay, 360, just making sure. It's kind of late, just making sure. So here we have 90, 90, A and theta. So here we have, 90, 90, well, theta and A. So we also know that B plus A, since they're supplementary angles, is equal to 180. Doing a little bit of algebra, we see that B must be equal to theta. Who doesn't love a similar triangle? I'm glad somebody said, I don't love them, so that's great, everybody loves them. So here we can think of our velocity vectors. Let's say the velocity vector magnitude is the same, and we have our angle theta, so we can set this similar triangle up to this one and do the ratio of the sides. So the ratio of this side here would be the change in velocity over v, the scalar, is equal to, well, this part, the length going from A to B, well, that's just your distance traveled. Your velocity times, how much time has passed, right? And divided by r. So we can set up this ratio given similar triangles. We also know that acceleration is equal to the change in velocity over change in time, which is also equal to, well, if we go here, we can pull this delta t down here, put the v over here. So we get delta v over delta t is equal to v squared over r. So we have this relationship. Who doesn't love force equals mass times acceleration? I don't know. As long as the mass is constant, it's all good. So we have this is equal to mass times acceleration, which is also v squared over r, or this the gravitational constant g is the mass of the Earth and the mass of your orbiting body divided by the distance squared. This leads, using that last equation, we can solve for v equal to the square root of g times m sub e over r. So we can get an idea, just a simplified view of how we can think about this orbital velocity. Now, there's a lot more things going on. This is oversimplified, obviously. You have a space shuttle. It's losing fuel. Hopefully things aren't falling off, right? Like heat chills and things like that. But you also have forces that are acting on it. You have speed, you have velocity. So there's a lot more that goes into play. One of the things that they talked about in the movie was this atmospheric reentry. And notice up here you see, Taraji Hansen playing Katherine Johnson working out the orbits. You can actually find these in the book too. Notice that the satellite here is following the circular path or elliptical orbit, and you kind of want to get it back to Earth safely following a parabolic path. So you can almost think of this as a piecewise function or splines where you're trying to link up an elliptical path to a parabolic path, but you don't want to crash and burn. That's bad. So the way that the rockets actually slow down is that the rockets literally turn around and fire in the direction that they're traveling in, so they slow down in that way. One of the issues is you could heat up because the atmosphere is very dense, so you have friction acting on the spacecraft. So yeah, that's not good if you go up into flames. So that is a concern. So here, imagine you're in a spacecraft. And you're coming along here, so here we have a velocity. We're going around on this path, but before we get to the perigee is the shortest distance, the closest point, the point on the path that's closest, let's say, to Earth, in this case, the O. And we need to slow down before that so we can enter into this parabolic trajectory and land safely. The dots around the circle, that's the atmosphere. So what's the velocity? What are the angles needed? And what does that geometry look like? So note that this picture looks strikingly similar to that one, huh? This is actually a screenshot from the book. This is another screenshot from that same book, and you see her drawing that picture on the board here in the movie. So the idea is, let's say if you're coming here, and let's say if you don't slow down enough, you kind of skip over the Earth and end up going off into space. That's kind of no good, right? But if you put the brakes on too hard in your rocket, you could undershoot and just crash into the Earth, and that's not good. So you have this entry corridor that you want to travel in so you can land in a big, let's say, body of water like an ocean, perhaps, right? And they use a lot of conics to do that. Now, at the beginning of the movie, we saw the young Katherine Johnson solving this equation. Now, I don't know, everybody loves to solve a polynomial, right? I mean, that's kind of fun. Was she really solving this? No idea. They said, Rudy, what was Katherine solving when she was a kid? Polynomials, right? And so this was actually his handwriting, but he said that the director said that his handwriting was so bad, that was the only handwriting that appears in the movie. We've all been in that class where you go, what is on that board? Yeah. Mm-hmm. So what did Katherine, why did she go into this field of education? Well, her parents are Joshua and Joylette Coleman, and her father was a farmer, and her mother was a teacher, a born teacher. Where they lived at in White Sulphur Springs, West Virginia, if you were black, you could not go to school past the 8th grade. So her father, farmer, so he probably did not have that much money, uprooted the family and moved them 120 miles away just so she and her siblings could go to high school. They were that dedicated to her education. So I think that dedication really shows in Katherine's work. And of course, who doesn't love school and math? So when Katherine was 15 years old, she started at West Virginia State College, which is a historically black college in West Virginia. And she just dove into mathematics. Fortunately for her, William Claytor started at West Virginia State College that same year as a professor. Now, I have to talk about my Howard people, right? So William Claytor is a Howard graduate. So he got his bachelor's, he grew up down the street from Howard, he's from the U Street area. He got his bachelor's from Howard, and then he also graduated top of his class in our inaugural master's program. He then went off to UPenn to pursue a PhD in mathematics. His advisor loved John Klein, was great. It was in the area of topology. People loved his thesis. Nobody reads PhD, well, some people read PhD theses, but not often people say, wow, that PhD thesis is great, right? So if somebody actually says it, that's a really big thing. Everybody loved his thesis. He was doing really inaugural work. He was the third black to get a PhD in mathematics. He could not get a job. He was in the field of topology, which is the same field of Robert Moore. His research advisor, Klein, was a student of Robert Moore. Robert Moore did not like black students at all. He didn't let him in the classroom. He thought it was a bad idea to integrate. And word got out that he was black, and it is told that basically Robert Moore blocked him from getting any job. He applied to go to the Institute of Advanced Studies, couldn't go. He ended up going to University of Michigan, couldn't participate in any of the research seminars. A couple weeks ago, at an event on the Hill, I ran into Katherine Johnson's daughters. Really pleasure to meet them. And they said that he really died of a broken, I would say, mathematical heart because there were so many blocks against his career. He's the first African American to publish a research paper. I mean, he just was hardcore coming up, but he just kept getting blocked. So, pity for him, but really good for Katherine Johnson to have this hardcore researcher as her mentor, because he created courses just for her. And it was through his research work is where which laid the foundation for her to be a research mathematician. He eventually did come and join the faculty at Howard in 1947, but he was pretty heartbroken. But I'm glad that he did train Katherine Johnson. The story goes is that he told Katherine, he said, "You're going to make a great research mathematician." She says, "Well, who's going to hire me?" He says, "I don't know. That's your problem." So he was great. When we watched the film, and I say we, mathematicians here, all of us together, did anybody question Euler's method? Yeah, okay. Just wondering.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method?
Yes.
That's ancient.
But it works. It works numerically.
That's it.
Let's type it up.
So people wondered, Euler's method, that's only good for order 1. Can I at least get an order 4 with Verga or some other method that works? So did she really use Euler's method? Okay, what really happened was they needed some, every film has that climax. And it's going to be Euler's method if it's math, right? Just kidding. And Rudy said, well, what about Euler's method? They were like, oh, that sounds great. so they just ran with it, put it in the film, and we're happy in the mathematics community because now people will stop saying Euler. so that was great. Now we know how to say it. Okay, so did she really use it? Maybe, maybe not. So that's kind of how we were all looking in the film when we were. Really? I don't know. But okay, so she did use approximation techniques. So this on the left-hand side is a report that she did, determination of azimuth angle at burnout for placing a satellite over selected Earth position. So let's say here's your satellite, here's your Earth, and if it rotates, in this paper she actually did calculations for going around Earth, like say 3 times, and Earth is kind of doing its thing, right? And if you wanted to, burnout means you stop firing the rocket, so it's just kind of in free form, and you assume that the only force is the one due to gravity. So let's just look at a little bit what she did in this paper. So in this paper, it's a lot of trig. If you love trig, there's a lot of trig going on there. You could probably spend weeks doing that. I did a day, and I was like, okay, that's good. I shouldn't say that. So imagine. So if you think Calc 3, right, and the spherical coordinates, here's your satellite up here. So you have here's the North Pole. So the azimuth angle is going from the north over to the horizon. It's that angle. But then you have the elevation going up, right? In Calc 3, we usually go down this way, right? But then we also have the distance out to the object. Well, it's kind of like, well, you know where the object, you just want to know where the object is. So you just need 2. You just need the azimuth angle and the elevation angle. So they were trying to calculate what those are to get that satellite over certain parts of the Earth after a couple of, let's say, passes around. So here, let's say we're at burnout, so you shut off your rockets, and you're kind of going around the Earth, and notice that it's going to wiggle around the Earth just because of how Earth rotates, and I can't really do it because my arm would fall off if I did. So imagine it goes down here, follow the top path here, and then it goes right here on the middle path, and you follow the middle path, right? So imagine 3 passes around the Earth. So you're given a burnout position, so you know where you're going to turn off the rockets, and you want to pass it over this, let's say this phi2, lambda 2 after n orbits, right? And so you want it here, but then you have an equivalent position here that has the same latitude, note latitudes here, but you kind of have to make an adjustment on the longitude just because of the Earth's obliqueness. It's not really a sphere, right? Just sorry to spoil that for you. So you kind of have to make up for it. So we start off with this equation down here so we can find this lambda 2e. So we get to take the lambda 2. T is the number of the satellite period, and omega e, that's the angular velocity of the Earth. Now, okay, so y'all know she has Barbie doll, right? How cool is that? How many mathematicians have their own Barbie doll made after them? Seriously. Okay, so if you're given a burnout position, and you wanted to pass over selected position after, let's say, n times, n orbits. So you have a starting guess value, right? So you can think of this, if you've taken numerical analysis, you have this fixed point. You want to plug something in, and you kind of calculate, and you go around, and you keep plugging stuff in until things converge and settle down. So we have a starting guess here, so we can plug it into this equation. And then once we have those values, and you know lambda 1, right? That's what you're given. That's when you know you're going to shut things off. So now you have this difference, and you can plug it in here. Then you can get this delta lambda 1 minus 2e. That's our adjustment. And now we can find the phi 1 and phi 2 and evaluate this one. It has a lot of equations, and they're based on a lot of laws. The idea is you want to get this, this t theta sub 2e. But what you do is you actually plug it back in so that repeat from the Pellegrene. so that your equivalent position, the equivalent position is this position here, the theta 2e converges. Now, once you get the theta 2e to converge, then we have these expressions where we can plug it in, so we can get the azimuth angle, psi 1, and also the inclination angle I. Again, that's the azimuth angle and the inclination angle, so you know where it will be. And you have to adjust for the obliqueness of the Earth on each pass. And when I go back to teaching, I just want to have some students just work through this in detail. I think this will be a lot of fun. But, if you're interested, there is a Wolfram Alpha, somebody has a workbook on this online where they actually work through the calculations. But it's never anything like going through it yourself, right? So notice here that we have the thetas of 2e, and it starts to settle down actually quite quickly, right? After just like a couple of iterations, which is pretty neat. And so it kind of settles down, so you can say, here are approximately the final values. And these are calculations from her paper that she did. So did she use Euler's method? Maybe, I don't know. But she did use iterative techniques in calculating. And I don't know about you, but I'm not sure if I really want to do all this by hand, but that's what they did back in the day, right? But they also knew the log tables, and the sine and cosine values of a lot of numbers. I like my phone, right? So Katherine Johnson recently, there was a building named after her at NASA, the Katherine Johnson Computational Research Facility, that opened in 2017. And in 2015, she earned a Medal of Freedom award from Obama. Obama, he's actually said that if you think your job is hard, her job meant if you didn't carry the one, you would end up out in space. So, it's all relative, I suppose. And just recently, this is November 20th, 2018, in the House of Representatives, they actually had an act, I think it's passed on both sides now, to commemorate Dorothy Vaughan, Katherine Johnson, Mary Jackson, and Christine Darden, who's featured in the book. She doesn't appear in the movie, but she's featured in the book. And they just had, Nancy Pelosi just had a thing on the Hill to honor them. So this is the last clip I'll play.
Hampton High School is a white school, Mrs. Jackson.
Yes, Your Honor, I'm aware of that.
Virginia, still a segregated state.
Your Honor, you of all people should understand the importance of being first.
How's that, Mrs. Jackson?
Well, you were the first in your family to serve in the armed forces, U.S. Navy, the first to attend university.
What's the point?
I plan on being an engineer at NASA. But I can't do that without taking them classes at that all-white high school. And I can't change the color of my skin. So I have no choice but to be the first, which I can't do without you, sir. Your Honor, out of all the cases you're gonna hear today, which one is gonna matter 100 years from now? Which one is gonna make you the first?
Could you imagine standing in front of a judge in a court of law, to petition to just take courses because the job in which you have keeps raising the bar? I mean, I kind of been there, but not in front of a judge, literally, so I know what she's talking about. But, I mean, so she really had to petition a judge so she could actually take courses to be an engineer. And she did, and she was an engineer at NASA, Mary Jackson. So the idea of being the first to do something, that really kind of hit home for me. So I graduated with a PhD in mathematics from the University of Connecticut in 2001. When I first entered UConn, they were like, what country are you from? Where are you, it's like, Indiana, hello. So it kind of dawned on me, maybe I should ask some questions. I was the first US Black to come into the math PhD program, and I was also the first to graduate. And so does it mean that I'm special? No, it just means that maybe there are some obstacles or barriers or social happenings that should be addressed. I'll put it that way. So in the year I graduated my PhD, so Black, and then here's female. So US Black, there were 6. So I joined a cohort of 6 other Black females in the whole country to earn a PhD in math, and then also 6 US Black males. And unfortunately, the numbers they haven't changed much. So I think there's a lot of work to do when you talk about underrepresentation, in particularly in the area of mathematics, so that people don't have to trudge through and be the first. Because I have friends, they'll say, I'm not trying to be the first. I know what kind of crap you have to go through. You know, because you get it first, and then hopefully you pave the way for people after you. But it's not an easy endeavor. However, once you come through, I have had a lot of fun doing mathematics. As she said, I did my undergraduate research. I ended up doing option pricing. My initial project was looking at difference equations, which is kind of what I'll talk about, will lead into what I'm talking about tomorrow. So it's an interesting continuum, and so that's me in undergrad. Hopefully I haven't changed much. When I presented my research as a poster, but you notice my friend's in a suit and I'm in a t-shirt? Yeah. So that was me as an undergrad presenting research, and then this is Shea Adekanye. He was my first graduate student, and so at Howard, I'm the first Black female to graduate a PhD student in mathematics. How long have we been around? Right, and so he's at JP Morgan doing cybersecurity and employing machine learning techniques in cybersecurity. A lot of fun. And she's pursuing mathematics. So it's kind of fun just to do the math, inspire other people to do the math. I recently was featured on NSF's Women's Making History Makers video. It's kind of fun. And in spare time, I coach my kids' basketball teams. So there's kind of a lot of dimensions. But you know, you make the life fun. So I like to end with this slide because oftentimes in mathematics, things can get hard. And sometimes we can think, oh, it's just me. But I was encouraged, like when things get hard, reach out, talk with people. It can be rewarding. It can be frustrating, but it can also be a lot of fun. So I hope this kind of gives you a little bit more insight into the mathematics of the hidden figures. And tomorrow, I look forward to sharing the stories, the non-standard finite difference games. Thank you. There's one more slide. And so Rudy Horn passed away in 2017, early. He was only 49 years old. And so I get choked up every time I say this. But that really sent really shockwaves through the whole mathematical community, that somebody that young, ambitious, outgoing, would die that young. But fortunately for us, he was able to share Katherine's story through the mathematics and give us Euler's method. So, yeah. Any questions? And you can ask anything.
Have you met Katherine Johnson?
I have.
She's still living, yes?
She's still living. And I hear she's an avid card player, right? You know, yeah, you can see that. So I haven't met her, but I met her daughters the other week on the Hill. Yeah, and they're really nice. You can see Katherine in their faces and things. But it was interesting when I told him I was a mathematician at Howard. William Claytor is our graduate. He was a faculty member. The first thing they say that he was so heartbroken. And I was just like, oh, so hard. But yeah. I met the family.
Does anybody have any other questions?
I understand that there are challenges both for women in mathematics and for African Americans. Did you feel that one of those was more of a barrier for your career or your opportunities?
So the word I guess they use is, you know, we like Venn diagrams, intersections. They call it intersectionality, when you kind of have both of them. And if you have a read the paper, there's a paper by Shirley Malcolm, 1972. She's at AAAS now. The paper's entitled The Double Bind, The Price of Being a Minority Woman in STEM. And when I read that paper now, it's the same story that they say then. So they say that women of color, you know, we have this confounding effect, you know, not only the gender, but then also the race. But in different contexts, people will, I don't want to say harp on, but I can tell that the woman part is more of an issue. Or in other circles, the black part is more of an issue. Or if somebody can't figure out my race or ethnicity, whatever they think it is could be the issue, right? You know, because I have this kind of chameleon look sometimes, depending on the time of year. So it really depends. But, I told a story. One time it was at a meeting, advisory group, and we were talking about women in mathematics, but it was just women, all women. I was like, oh, I'm getting tired at this meeting. Why am I getting tired? At the reception, somebody said, I like how every time they cut you off, you just keep on talking. I said, oh, that's why I'm tired. Because I'm like, it's like a lot of energy just to participate, because So I was like, thank you. But for me, I find that people giving me that honest feedback, I'm seeing this is happening, because sometimes I don't see it, because I'm too busy in the mix or just trying to get, be incorporated, what have you. So it's nice to have the advocates who can, shine a light to give a voice to that reality that sometimes we think is me, or we internalize, that sort of thing. So it really depends on the circle. But I'll catch the heat from, I'll catch the heat from all genders and races. It does, yeah. But it depends on their viewpoint. Typically, though, like if you go back to the literature with bell hooks, black female, usually we do the race first and the gender second, right? It's a little bit of it's a different ordering. And in the black community, it's kind of understood that black females take a leadership role. So there's a little bit of a different aspect and different approach to it. But in different situations, I'll get treated differently and definitely talked over. If I say I have an idea about something, somebody else says the same thing. Oh, theirs is good, but mine is suspect. Oh, I don't like the tone of your email. I get that. Oh, you're ambitious. Yeah, I'll get that too. So sometimes I have to have a really good filter to determine, is this really valid feedback, or is this laced with something that has nothing to do with me? Hope that answers. Yeah.
Thank you. I'm a pure mathematician, but most of the math here didn't scare me a whole lot. How much did Katherine Johnson and her colleagues have to deal with in terms of dealing with fuel loss and dealing with the fact that the wind might be moving at different velocities at different points of the atmosphere? Because that sounds horrible if they have to do that stuff by hand.
Yeah, and they did do a lot of the stuff by hand, but that's where they were called computers. And actually, it was commonplace at that time for African-American women to be computers in different federal agencies, right? Not just NASA. So, I mean, whenever we talk about, let's say, mathematical modeling, because to a certain extent, that's really what it is, you can't take into account everything, but you need to take into account enough so that things don't crash and burn. So you might have an epsilon error, but as long as that margin of error is not too great, it may be okay. So, but you do need to look at the weather. You do need to look at the fuel loss. You do need to look at velocity, trajectory, path, oceans nice and wide, and where you want to go. So they did take into account those phenomenon, but as any good mathematical modeler will tell you, we can't take into account everything. But hopefully we take into account enough that things will work out.
Did they have a sense that they were within the proper epsilon while they were doing it, or were they just kind of crossing their fingers and hoping that John might come back?
I wasn't there when it happened. So, I'm still 20-something, kidding. But I would guess that I think there was crossing of the fingers. In the movie, you'll see that John Glenn said, get the girl to check the numbers. And he meant Katherine Johnson. So he knew who she was. And so to imagine this astronaut, get her, I want this one person, not anybody else, one person to check the numbers, meant that they had a lot of trust in her. That's a lot of trust you put in one person to check them. It took her 3 days to check those numbers and get them out, get them right. So I think there was a bit of a panic. I believe there was a lot of panic at that time. But I mean, you just work diligently to hopefully you have something that is feasible. Yeah.
I thought of another one. I can imagine that some people would think that Katherine Johnson wasn't really a mathematician, that she wasn't creative, and yet I think she was. But do you get that? Do people actually say things like that?
I shouldn't say this, but so the event on the Hill that Pelosi had, right? the reception. It was a nice reception. It's very lovely. She called them all mathematicians. I was like, yes, even though they weren't really all mathematicians, right? They were engineers and computer scientists, right? I was like, yes, call them all mathematicians. But I don't get a sense that people are saying that she's not a mathematician. I get a sense that people, I mean, she has work, she has reports where they're using mathematics. So if you were to, I guess, categorize, she'd be an applied mathematician, right? Maybe computation, bordering, interplaying with physics, right? But no, I have a feeling people really are seeing her as a mathematician. I don't think somebody needs to have a PhD to be a mathematician. I'm not saying that we know any PhDs that, are suspect, but, the degree doesn't, the degree doesn't determine one's ability and their contribution that they can make. So I at least in the circles that I've traversed in, people accept her as a mathematician.
So I'm a math education major, and one of the things in my classroom, I want to connect my students with the history of math, right. And I kind of get tired of saying white guys' names as I'm telling these stories. So I'm wondering, do you have any recommendations for additional resources for people of color or women mathematicians that have maybe kind of not quite hit the mainstream, but have been like riding the wave along with the story of Katherine Johnson that's as it's become known?
Where are people? I'll answer that, but can I throw a different question in there?
Sure.
And why are these figures hidden? Is that kind of the question in there too?
Yeah.
Why are people hidden? So I'll answer both. So I'll answer your question first, and then I'll answer my question second, if that makes any sense. I have no idea. So your question first is the person holding the mic. She has a great poster on the outside of her office. And so there's a website, Mathematically Gifted in Black. So they feature a new person every day over the month of February for Black History Month. So Mathematically Gifted in Black. You also have the Lat Math, Latinos in Math, right? Where they also highlight and feature Latinos. And that should be coming up.
And SACNAS.
And SACNAS. SACNAS will be in the fall. They have the Modern Math Workshop at the SACNAS conference on the Wednesday. And let's see, I'm giving a talk at the National Math Festival. So it's kind of like, so I get what you're saying, that you really do kind of have, like I know these people, right? They're all my friends, so I just kind of take them all for granted, right? I shouldn't take my friends for granted. So I get it, yeah. But so I would look at Mathematically Gifted in Black, the Lat Math, and the American Mathematical Society has posters that you can get for free on women, African Americans, Latinos, Hispanics in mathematics. So the American if you can't find the page, let me know, and I can find that for you. So sometimes that's nice to just have on display, right? So I hope that helps, but now I'm going to answer the other question. Why is this whole thing of hidden, why is that a thing? In the STEM community, this whole public outreach and public engagement, that's new. That really is frowned upon in the profession, in the STEM community. It's almost like you're not taking your science seriously if you're out doing that other stuff, which is not seen as science. So making your science relatable and accessible to the public, like Neil deGrasse Tyson, I think he has a lot of haters, so to speak. People have taken his work and tried to deflate it and saying, well, what's the value? Why should you do it? That sort of thing. He should just stick to doing science. Why is he worried about engaging the public in anything? So we have, I don't know if it's crabs in the barrel, pulling other people down, or snobbery in STEM, but in the STEM profession, we traditionally have not valued outreach. We have not valued engagement with the public. That's a new thing. And I always tell young people to be careful, because that could kill your career, because people will take you less seriously. It's just weird, I don't know, But so I think that we have this hidden thing in mathematics just because it's not of the value system traditionally. So it's kind of like if you go out there, you really go out there kind of on the gauntlet, so to speak.
I think we have time for one more question.
Oh, you can also check out my webpage too, TalithaWashington.com.
Just a related question to that, as you mentioned that the STEM fields, previously didn't acknowledge the public as well.
Yeah, currently too, yeah.
Yeah. Now, adding on to that, general culture seems to not find math important. So how do we, as math educators, try to utilize any resources that are out there to enhance that with our students?
Yeah, the role of the public intellectual. Yeah, it's a hard one right now. I mean, it is a hard one. I think that people are saying, monetarily wise, if you don't tell your science story, funding could be an issue, right? So I think that there are coalitions, there are groups that are really pushing and advocating that scientists really share their stories, because if we don't, we're not in a post-Sputnik era anymore. Government, what have you, they're not just throwing money, right? That's not happening right now. So I think that people are becoming more engaged. I think that if you wait for the scientists, let's say, to do the proper engagement that you're looking for, I don't think it's going to happen in our lifetimes. It's not going to happen, but then how do you tap into that? So it's an interesting concept. Could the mathematics educators, could they fill in that void? Could they fill in that space for us? Sure. I don't know if you're familiar with the Benjamin Banneker Society. That's another one. I should have named that too. The Benjamin Banneker Society, it's focused on African Americans, K through 12 teachers. They do a lot of really good work centered around the math education, right? And also diverse populations. I just I used to get in trouble for talking as a kid, like in school. I kind of had a lot of mouth. And so now I say, I just keep using it. I recognize that by using my voice, it could be detrimental, so I have to be careful. But in my theory, if I don't do it, who's going to do it? It should be done somehow. But I understand the risk. So could the education community help fill in that gap and fill in that void? I think so. Because I think in the education, there's a lot more educating all that comes naturally out of the mathematics education group versus, let's say, the traditional mathematical sciences group, if that makes any sense. Yeah, that'd be great.
Thank you very much, Talitha. This has been a wonderful evening, and I'm sure that the conversation can continue over pizza, which is here. So let's thank Talitha again.